So to round out Unit 2, we're going to discuss parametric equations, which kind of just sounds weird to be like switching over to Chapter 10, but all of this is kind of applications of what calculus can do, right? So in Chapter 7, we learned about area between two curves and volumes of revolution. And here we're going to take a different turn and talk about what else calculus can do and this new graphing system, which is parametric equations. So I just wanted to give you some background for like, why does anybody want to talk about parametric equations, or why do we need it? In this example here, this is what you likely have seen in an advanced algebra class or pre-calculus. And so just this little example here of an application problem, right? So we've got this description, this equation that describes the path of a ball thrown by a child. So you could imagine, here's the child. I'm just going to draw, and they're throwing their baseball. Maybe their arm is up here, I guess, right? And so the x-axis is what they're showing as being the horizontal distance from the person throwing the ball, right? The child throwing the ball. So I'm going to label this as the horizontal distance. And they describe, y is the height of the ball. I'm going to call that vertical distance, just for the sake of having something different, right? So there's your y-axis, and this is your vertical distance, which is great. You can definitely use this equation to describe the path of this ball as it's being thrown. I can, kind of identify an important point, right? Probably back in your advanced algebra and pre-calculus classes, you talked a lot about the maximum location. I'm just going to eyeball that as 2, 6. That's the maximum of that particular ball that's being thrown. So if I just kind of like piece that out and talk about that's the maximum location of that equation, right? But this only tells me a couple of things. It tells me that the maximum occurs. Let's see. It says the maximum occurs when the ball is 2 feet away from the child in the horizontal path. And then the 6 is what's telling me, oh, okay, well, that maximum occurs when the ball is 6 feet from the ground. So that's the maximum of the ball. It occurs when the ball is 2 feet away from the child in the horizontal distance, and it's 6 feet above the ground in the vertical distance. What I'm missing here, which a lot of times I would probably like to know, is I'm sort of missing, another feature of this, which is how about time? How about when? When does the ball reach its maximum height? I'm sort of losing that in this situation. I don't have that information. I would really like some indicator of time. Can I get any kind of time going on in this situation? And the answer is yes, you could, if you sort of just convert this equation or reimagine this equation, which is a parabola, right? But instead of writing it as y as a function of x, where you only have 2 parameters, right? You only have 2 variables. You've got y and you've got x. What if I change this over into parametric equations, which is what you see down here, which is really designed to give you that extra parameter, that extra variable that you so wish you had in that last example. You've got horizontal distance, you've got vertical distance, which is great, but if only you could have a t variable to indicate time, that would be awesome. So that's what parametric equations do for us. It actually takes the information, and you can have 2 separate equations, one that will evaluate the horizontal distance and one that will evaluate the vertical distance. And independently, these are both functions of time. So you get that extra parameter that you were looking for. So these are often called a plane curve, denoted by, a capital C. All right, just if you see that, in future classes. And our parameter, it can either take on a t, most notably time, especially in physics and stuff like that. It could also be an angle. So it could, if you're involving trig, we could use t, but you could also see a theta. You could see like x as being f of theta or y being g of theta. So they're independent functions of a different variable. And that's like your timekeeper in a way of that extra parameter. So it allows us to talk about more complicated graphs. And if you see down here, this is a quirky question, right? Quirky situation. This is certainly not, if I look at this graph completely fails that vertical line test to say like, hey, is this a function? Well, here it passes, right? But here, oh dear, I've got that vertical line crossing in 3 locations. This is not a function. This is not y as a function of x. You get a lot of different images that will take shape here. This is a lovely graph. And so here is the set of parametric equations that defines that graph, that sort of creates that graph. And so we are talking about the flight of a paper airplane, if you can imagine throwing it up. I'm not sure my paper airplane would do a loop-de-loop, but so be it. This is what it is, right? And here is that parameter time t. It's denoted as being time. Often it is. It doesn't have to be. And they give you a range of where it's appropriate. How long did this, how long does this model work? For the situation. And this is describing, hey, x is the distance away from the start in feet, and y is the vertical distance away from the start in feet. And you get that indication of time, which is helpful. So you can answer things like, well, where does this plane start? Like, where is it at t equals 0? Let's just start with that. Where is the plane? Where is the paper airplane at the start, at the initial location, at t equals 0? You can actually describe that like, well, at the minute when you kind of threw this paper airplane, I kind of see it there from the graph. Let's plug into our set of parametric equations. X is t minus 3 sine t. So what does that mean? Well, it's going to be 0 minus 3 times the sine of 0. The sine of 0 is 0, so there's that. And then y is 4 minus 3 times the cosine of 0. So the cosine of 0 is 1. And so I can see exactly where it is. I have an actual ordered pair on the xy plane. 0, 1 is where this particular airplane starts. And I can see that pretty reasonably there from my picture. There's t equals 0. That's the beginning path of this airplane. And parametric equations have a path. They have an orientation. They have a direction. It's not a two-way street here. So what I'll do is kind of do the same thing. Let's find out where is the plane. Where is the paper airplane? At t equals, let's just say pi over 2. Since we're dealing with trig, let's go with really nice evaluations here. Well, x is going to be, what is that? Pi over 2 minus 3 times the sine of pi over 2. Pi over 2 minus 3. So that's a negative value because pi over 2 is around 1.7. So 1.57. 1.57 minus 3 is something negative, right? So it's a negative value. And then over here, 4 minus 3 times the cosine of pi over 2. The cosine of pi over 2 is 0. So at pi over 2, it looks like my ordered pair is, well, a little smidge negative there, and then a y value of 4. Right here. That's where it is at pi over 2. So you can see that this thing has a path, it has a movement. It's moving in this direction. So this is the flight of that paper airplane all the way through this process. So you just kind of handle like more interesting things with these parametric equations. Okay, in the next video, I'll show you how to graph them and maybe convert parametric equations to a regular, what we would consider a rectangular equation. This one does not have a rectangular counterpart. It's such a quirky graph. Not every set of parametric equations can be rewritten as a set of rectangular equations. but some of them do. So we'll handle that in the next video. I just wanted to give a little introduction for why do we need a new set of equations to graph. So hopefully that works.